All right, so let's go ahead and get this going here. Yeah. So I guess the first thing we'll do is we'll look at the lab. This is law, page 39. Uh-huh.
In the manual, it says to look at your calculator to see if you have a plateau.
Mm-hmm.
I remember last time we just tried to supposed just to look at it. Is it be there or?
It's going to be there. Usually after it does a time lapse one, then it will say, press enter to display the graph, but it'll show you that. So let me look at the settings on this. This is the first question that we had. So again, the reactions where we have a solid, we probably do want to collect for a longer period of time than the one where we start with two solutions, because we have to wait for the solid to dissolve to get a full reaction out of it. So you're setting it up the same way that you did last time with your specific heat thing, but your time frame is different. So for reactions 1 and 2, you're using 10 minutes. So 5 is the time between samples. Use 120 samples, which gives us 10 minutes. Then for reaction 2, no changes there. That's where I'm looking at it.
3.3 minutes up in reaction 1.
That's right. Oh, reaction 3. Okay, so yeah. So all of the other one, 5.83, the other ones are 10 minutes.
Because it has 3.3 minutes up. If you scroll up for reaction 1, is it right? Step 9. It says the second to last.
No, it says after 3.3.
If I have 120 samples, and I know that for every one sample, there's 5 seconds, then it's going to be 600 seconds, which is 10 minutes.
Right.
So, okay, I'm just trying to make sure that.
Yeah, I get that.
No, I'm doing this for me. Press the enter to begin data table, reaction 1. You're right, this one is incorrect. It should be 10 minutes. And again, you want that 10 minutes, because if you don't, yeah, within 10 minutes, you should have a plateau. But the third one, I reduced the number of samples so that it wouldn't take as long. So for the third experiment, so this one should also take 10 minutes. This one should go a little bit faster, but just in case, we're going to give it 10 minutes. And the last one, if you have 70 samples, and we have 5 seconds per sample, that means we have 350 seconds. Even I can do that math. 6 goes into 35. What, 5 times? Yeah. Minutes and 5, 6. So 5.83 minutes is fine. So yeah, that's okay. So it's just there's a typo in the reaction 1. Thank you for asking. And I'm glad you mentioned it, because it'll remind me to fix it before I teach this next year, because I teach it in the summer and I don't usually teach it in the fall. All right. Trying to think if there's anything else. Calculations to show. Pre-lab. Read the sections. That's a good idea, because we've already actually talked about that. It tells you that the data table is kind of nice, but if you don't read the experiment, there's going to be lots of extra crap in there. And I'm going to mock you. I'll guarantee you I will mock you when I see your lab notebook. Why do you have all this? Because you didn't need that. That's not part of your experiment. So that's the price you pay for that. In experiment 2, we are looking for limiting reactants. And so, yeah. So, yeah, didn't see anywhere where I have omitted answering those questions. So now I have to look at my quiz to see why it said that. I'm fascinated to why it said that.
I would know the functions part too that you had to go find
Mhm.
out.
Yeah. So you definitely should be doing that because that's sort of helpful to you. Anytime I have you do a pre-lab calculation, it's because it will help you once you get into lab. Yeah, Brandy?
In the quiz, the first question said like, which of 4 experiments are we not doing? There's only like 3.
There's only 3
So the
experiments.
lab manual says you use your CPAL from the previous experiment that we did, but the first
Right.
question seemed to make it seem like
Ah, okay. I'm seeing a real trend here. I had to import, you remember all these quizzes in from Blackboard. It looks like you got one for the one I imported was a version from like 3 years ago. We used to do the calorimeter experiment on all of them in the same lab, and it took forever, and everybody was just super stressed. So that's why I split the lab into 2. And the quiz I obviously gave you was one that was from a few years ago. So I will 86 the quiz. No, don't stress it. You're good. Thank you for asking about that. Okay, so now I'm understanding what's going on there because yeah, we haven't done the calorimeter constant with it in a long time. So I apologize for that. I didn't recognize that. So the experiment itself is very straightforward. You are going to start out in experiment 1 with water, and you're going to add sodium hydroxide to it, and you're going to figure out how much heat that generates. Just like the first experiment, you're going to start it for 1 minute with a probe in the water. Probe in the water, and then add the sodium hydroxide so that you're going to see the jump for the line of mixing. Second experiment, you're going to start out with HCl solution in the water, and you're going to add sodium hydroxide to that. So you need 1 minute here while the program's running, then add the solid, let it run out. Both of those should take 10 minutes. Third experiment, you have HCl solution in the cup, different concentration, and that was something that we were mentioning earlier. Make sure that you get the correct concentration because there will be 2 bottles on the cart. So make sure you get the correct concentration. You're going to have that in the cup for a minute, and then you're going to add sodium hydroxide solution and let it run out. And that one's the one that only runs for like 6 minutes, 5.83 minutes. So it's a pretty straightforward experiment. You just need to be conscientious about allowing that first minute of data. If you don't do the first minute of data and you add it immediately, I'm going to make you redo it. And so just a heads up on that. Anything that you had to mass or record a volume or a concentration for should probably be in your lab notebook. All the temperature readings are going to be on the CBL because you're using the temperature probe. Yeah.
Are we doing the setup probe where you let it stand?
Yeah, that's just always a good idea because it gets it out of the way. But since you don't have a hot plate this time, it doesn't really, well, you have a stirrer function, but we're not using the heat. So having the wires out of the way is just a good protocol in general. But it's not as vital as the first time around. And any other questions about this part? Again, we're going to put a little pellet in here, which is your stir bar. I 86'd them on the first lab just because you were still learning how to deal with the CBL process. The other advantage to having the probe suspended is that you can keep it up a little bit away from where the stir bar is actually working, because you don't want the stir bar to hit the probe when you're taking measurements. The stir bar runs on the hot plate. Again, there's one that says hot heat and the other one that says 0 to 10 fast and slow. You want to be sure to use the one that's talking about fast and slow because we're not heating anything today. And what this has is a magnetic bar that spins, and it causes the little stir bar to spin and mix it. It does a much more uniform job of mixing than you would. And in this reaction specifically, you need a faster response time for the reaction. So it's going to make the reaction go a little bit faster just by stirring it, and it's going to do a better job of getting that solid to dissolve. So anything else on the lab you're doing? Okie dokie. So let's go ahead and look where we were last time. We were talking about Dalton's law, and Dalton's law was the gas law that talks about mixtures. We looked at only the first situation where we were looking at gases that were collected over water, or at mixtures of gases, and yes, it's page 47. Today we're going to look at a couple different other versions of Dalton's law. If you think about it, what Dalton said is that if I have several gases, the pressures are additive. And I know that pressure for any gas times the volume of that gas has to equal nRT. So if I'm talking about gas A, that would equal moles of gas A times R times the temperature over the volume. And that would be true whether I was talking about gas A or gas B or gas C. It would just be that the pressure depends on the moles of that stuff. Because in a mixture, the volume of the container and the temperature conditions are the same for all the gases. So I could say that the pressure total was a function of factoring out my constants, RT over V, moles of A plus moles of B plus moles of C, that the total pressure is a function of the fact that I have differing amounts of each thing. Now, this is one version of Dalton's law. It's usually written that pressure total equals times volume equals moles total times RT. So it looks like the ideal gas law. But I wanted you to understand where that comes from, that the moles total is the moles of each of the individual gases. Now, there's another version of this as well. If these things are a constant for everything in that mixture, then I could say that the pressure total over moles total would have to equal RT over V, which is a constant. Do you agree to that? And if this is a constant for every gas in the mixture, I could also say that it would equal the pressure of gas A over moles of gas A. Because gas A will expand to fill the whole container, and it's at the same temperature as the whole mixture. Or I could say that that would be true for gas B compared to the moles of that gas. That for all gases in the mixture, this ratio has got to equal the ratio for any other gas. It's not commonly written in this form. What you commonly see is this. So I'm just going to pick out two of them, total and gas A, which is just any of the gases in the mixture. If I want to solve for the pressure that gas A is contributing, then I could say that the pressure total times the fraction of moles is equal to the pressure of A. All I've done is move the moles of A over to the other side. Are you with me? Stop me if you are not. All I've done is I've taken this thing, which I know is equal to this constant. By transitive law, it means that this has to equal this. Because B equals B and B equals C, then A is equal to C. So they have to be equal to each other. And now all I've done is isolate that variable. Are we okay? For this reason. This fraction is symbolized mole fraction of A. So a mole fraction is just exactly what it sounds like. It's a ratio of moles. Moles total is on the denominator, and moles of any particular gas, of one of your component gases, goes on top. So I could have a mole fraction for gas A, I could have a mole fraction of gas B, I could have a mole fraction of gas C, whatever substance I have there. But big picture, if I look at it really carefully, I'm saying the part of the pressure that is due to gas A is because gas A makes only a fraction of the moles of the total pressure. That since gas A doesn't make up the entire mixture, since it's only a fraction of the entire mixture, it only contributes a fraction of the pressure. And so we're saying is we know how much of a fraction it's going to do because it's based on how many moles I have available. It's a mole ratio, moles of the component over the moles total. So mole fraction of substance A would be moles of A over moles total. If I wanted to talk about mole fraction of B, that would be moles of B over moles total. It's just a ratio of 2 moles, where the total is in the denominator. Now, which version of Dalton's law I use, because there's really 3 of them now. One of them says pressure total is the sum of the partial pressures. One of them says pressure total times volume equals moles total times RT. And one of them now says that the pressure total times the mole fraction is equal to the partial pressure of whatever the gas is. Which version I use just depends on what kind of information I'm given in my question. For example, in air, which is at sea level, roughly 1 atmosphere, 78% of it is nitrogen, and about 21% is due to oxygen. And usually there's a fair amount of argon and CO2 in the air. So the question first off is, what would be the mole fraction of nitrogen? Well, how many moles of nitrogen do I have? Well, what I have is a pressure. Would you agree to that? So I could say pressure total times the mole fraction of nitrogen would have to equal the partial pressure of nitrogen. Would you agree to that? So my mole fraction of nitrogen would be the pressure of nitrogen over pressure total. In this case, 0.7808 over 1. My mole fraction is 0.7808. So this time, since I was given partial pressures and I was given a total pressure and they just wanted to know what the mole fraction is, I know how the mole fraction relates. Are we okay so far? All right, so let's look at the next one. We have a mixture of gases. There's 5 each grams of neon, oxygen, and hydrogen, and I want to know what is the mole fraction of neon. Well, since I have grams, would you agree that I could find moles? Yeah, so let's go ahead and do that.
First one, just
Mhm.
real quick. So the mole fraction, would it be the 0.7808 over 1? Is that just the fraction?
Yeah, or you could write it with an implied denominator of 1.
Okay, so it's pretty much given, you're just asking so that we understand.
Well, I'm showing you that it was not given to you in the form of a mole fraction. It was given to you in the form of partial pressures.
Oh,
But you could relate it to solve for the mole fraction, right? This is a partial pressure. This is the pressure of nitrogen. This is the pressure total. And it's asking for the mole fraction. And so I'm able to relate that easily.
it's just because the
Yeah,
total was 1.
exactly. All right, so let's see. We've got a few substances here. We've got neon. We've got oxygen. We've got hydrogen. And what we know is that we have 5 grams of each. What's the molar mass of neon? All right, we got oxygen, which is 2 oxygen atoms. And we've got hydrogen gas, which is 2 hydrogens. And so I know the molar mass. So I can find the moles easily enough by taking my mass and dividing it by my molar mass. So the first portion of the question just said, what is the mole fraction? If I want to know the mole fraction, the mole fraction of neon, which I think is what it was asking for, sorry. Yeah. Is going to be the moles of neon, 0.24777 over the total moles, which apparently is 2.884. So my mole fraction is going to be the moles of neon over the total moles. If I wanted to know about oxygen, it would be the moles of oxygen over the total moles. How can I find the mole fraction of hydrogen easily? I could, but what do all fraction pieces have to add up to? All fractions. 1. You have 1 pi, you cut it up into 8 pieces. All the pieces will eventually make that 1 pi. So the last one I could always do by subtraction. 1 minus this, and also minus this one. So yes, you could also set it up. But you know the last one has to make up the rest of it. So fun fact about that, if they give you one and you need the other, the sum of all your mole fractions has to be 1, always. So we have a mole fraction for this one of 0.0859. Question then says, if we know that the partial pressure of neon is 1.0 psi, then what is the pressure total? Well, I know that my pressure total times the mole fraction has to equal the pressure of the individual, right? And we know the mole fraction, and we know the partial pressure, and so now we're just looking for the total pressure. Well, if we're only given the partial pressure for neon, and we have the mole fraction for neon, then I can find, because whatever my mole fraction for, whichever mole fraction I'm using, I have to relate to the partial pressure of the same stuff. So whichever gas I had chosen, I could figure out based on its partial pressure what the total would be if I knew the mole fraction. So I was given partial pressure of neon. I calculated the mole fraction, so I should be able to solve this fairly easily. My pressure total should be my partial pressure of neon divided by my mole fraction of neon. So apparently 11.64. And our units apparently are PSI because it was based on PSI.
With this formula, just know the mole fraction for one of the gases and figure out the total for all of them.
Yes.
Pressure for all of them.
Yes. And the reason that that works is because, let me go back up here a little bit. If every gas in any mixture would have to equal its moles times RT over V, and my total is the sum of all of every gas that's in the mixture, right? If they're all in the same container, then the temperature and volume would be the same for all of the gases in the container. So when I factor that out, I can see that my total pressure is a function of the individual moles. if I take this and just do the algebra to solve for the thing that's constant, then the pressure to mole ratio is equal to a constant for everything in that whole mixture, whichever gas I choose to pick out. So we chose this time to talk about neon, but I also could have talked about oxygen or hydrogen and figured out their partial pressures. So the big picture here is you know that you're going to be given these formulas. Your mission is to know how to use them. And so this is one version of Dalton's law that says you can sum the partial pressures. This is another version of Dalton's law that says the partial pressure of an individual is equal to the mole fraction times the total pressure. As long as you need, and this is the third version of it that says total pressure depends on the total moles. So which one you use just depends on what kind of information you're given in your question. Other big picture, let me zoom this out a little bit. Other big picture idea I want you to get from Dalton's law. Dalton's law is the only one that talks about mixtures of gases where they pick out the individuals. Air is a mixture, and as long as you don't care about any of the individual gases in there, you can talk about the entire mixture and its behaviors. But if you need to pick out one of the substances in that mixture, that's where Dalton's law comes in. It allows you to separate out the individual components. But we most of the time are dealing with mixtures. It's just that if you need to know about a component in that mixture, that's where Dalton's law comes in. Last one says, for a mixture of gases, the total pressure is the sum of all the gases. We got 5 grams of each of these. We want to know what's the total pressure at 50 degrees Celsius and 2.5 liters. Now, lucky for us, we just figured out our total number of moles, 2.884, in our last problem. And so the question is, what's the total pressure? Total pressure times V equals moles total times RT. So our total pressure is going to be moles total times RT over V. 2.884 moles times 0.082057 liters times atmospheres over moles times Kelvin. Our temperature was given as 50 degrees Celsius, but we would never even think about working in Celsius. Right? In fact, I won't even grade the question if you work it in Celsius. That tells me you don't understand gases at all. 50.0 plus 273.15. Be advised. It may ask you for an answer eventually in Celsius, but you have to work it in Kelvin. And we're going to divide by the volume of our container, which was 2.5 liters. Check your units to make sure you did your algebra correctly. Moles is on top and moles is on bottom, so it cancels. Liters is on top and on bottom, so it cancels. Kelvin's on bottom and top, so it cancels. And we're left in the unit of atmospheres, which makes sense for a total pressure. And apparently 30.04 atmospheres. Based on our sig figs, we had only 2 sig figs in our masses, which means that our moles could only ever have had 2 sig figs. So we're going to be good to the tenths place here on moles total. And we had temperature that was good to the tenths place. And our volume was good to the tenths place. So how many sig figs am I entitled to have? Just 2. Yeah, any factor that went into that. Stoichiometry does come into play when you're talking about gas laws. It's just that now we're looking at the big picture. When we talked about solids, if we have mass, we can divide our mass by our molar mass, and that'll give us moles. When we had solutions, we said we could take our liters and multiply it by our molarity, and that would give us moles. With gases, if PV equals nRT, then PV over RT would always give us our moles. And specifically at STP only, sorry about that. Oh, what I'm doing here. I know what hang on just a second. All right, and I've turned off some of the features of it, the pen and my other thing. I have to set up this computer to do that. All right. If you're at STP specifically, then the volume, if it's in liters, over 22.4 liters per mole would get you to moles. So this is a nice shortcut if you happen to be at STP. We're just not always at STP. So stoichiometry is stoichiometry. Step 1 is always find moles. Step 2 is to relate moles to moles. Step 3 is to go on to whatever it is they ask. It's just that now we have 3 different possibilities because we have 3 different states that we could be working with. But there is a nice little function about equations or about stoichiometry if you happen to have volumes. If you are talking about volumes, if I know that PV equals nRT, then PV over RT is N. That if they're in the same container, temperature and pressure are total pressure are constant, total R is constant. If they're in the same container, the mole fraction is going to be the same as the volume fraction. Let me show you why. I have 25 liters of hydrogen. Let's say for a second that we're at STP. I know that at STP, 22.4 liters would give me 1 mole of that substance. And I know, according to my stoichiometry, that for every 3 moles of hydrogen, there was 1 mole of nitrogen. Yes? And for every 1 mole of nitrogen at STP, there's 22.4 liters. Do you agree to that? You can see that the 22.4 number cancels. And now, instead of talking about a mole fraction, we're talking about a volume ratio. So instead of reading this as 1 mole reacts with 3 moles, I could say 1 liter reacts with 3 liters. If they're both gases, any gas occupies the same volume if it's the same amount of stuff. That's what Avogadro's law said. So when we use it in this form, it's called Gila-Sachs law of combining volumes, that says that you don't always have to go to molar mass. You don't have to do that all the time. If you are just comparing gases, very specifically things in the gas phase, you could use volume ratios in place of the mole ratios, because you're going to see that the conversion, any conversion you had to do to go from volume to moles, would be canceled out by the other substance, which would also have to undergo the same conversion. And so it's just a nice shortcut. So in answering the question, I could have just said, if I have 25 liters of hydrogen, for every 3 liters of hydrogen, I'm going to get 1 liter of nitrogen, 8.67 or something liters of nitrogen. Or I could have gone to moles and moles to moles and done it in 3 steps. Now I can do it in 1. So Gay-Lussac's law says if I am talking about a reaction, they're all in the same vessel under the same temperature and pressure conditions. Therefore, their moles and volume should be consistent. So they should be proportional. So I can do a quick stoichiometry if I happen to have volume. Second reaction here says, well, if I have 125 liters of hydrogen and I have 50 liters of nitrogen, I want to know how much ammonia I'm going to get. What kind of problem is this? Yeah. Uh-huh. Okay, you're right, you're right. Calculate the volume of, right, I was describing the problem. You're exactly right. 2/3. 2/3. Thank you. That's what was bothering me, 16.67. Thank you for asking. Absolutely, it's a limiting reactant. You have 2 starting quantities. It's just that, again, you can do the calculations very quickly, because I can say for every 3 liters of hydrogen, I'm going to make 2 liters of ammonia. And for every 1 liter of nitrogen, I'm going to make 2 liters of ammonia. And only one of those values can be true. Which one is it? Yeah, the 86. The other one was just good for comparison purposes. This is your theoretical yield, and this is your limiting reactant. This one is in excess, and this number is meaningless. Yes.
So this is only if it's at STP, like if it doesn't temperature.
No, it would work at any temperature, and here's why. 22.4 happens to be the molar volume at STP. However, there is a molar volume for every other possible condition. So if I had said I've got 25 liters of hydrogen, whatever the molar volume is in liters, that would be 1 mole. And then of hydrogen. Then if I wanted to relate it to ammonia, for every 3 moles of hydrogen, there's 2 moles of ammonia. And if I wanted to go back to volume, I would say for every 1 mole of ammonia, there's whatever that molar volume is for the conditions of liters of ammonia. So whatever that number is, maybe it's 22.4, maybe it's not, either version it's going to cancel. Because molar volume just means 1 RT over P. It means that we're always guaranteeing that that number is a 1 for the moles. So
But we're getting volume.
yeah, exactly, whatever that number turns out to be would cancel either way. And that's what Gay-Lussac's law is trying to say. When they mix and match, however, if you mix physical states, then you can't do that. However, stoichiometry still applies. It just means that you have to pay attention to the physical state you're working with this time. For example, we are decomposing 150 grams of sodium nitride. Oops. And the question says, how many liters at 1 atmosphere and 25 degrees Celsius? This is my unknown. This one I could find moles because I have the ability to figure out what the molar mass is. So starting with what I know, I have 150 grams of sodium nitride or sodium azide. Forget my number here. 22.98977 for the sodium and 3 times 14.0067. Apparently molar mass is 65.009 grams per mole of sodium azide. Now, how does that relate to the nitrogen? Yeah. For every 2 of the sodium azides, we're making 3 of the nitrogens. Are we okay there? So now we're talking about this substance. We now know how many moles. I know that what I'm looking for is liters, volume. PV equals nRT. Volume is going to be nRT over P. So we've got the moles. All of this now collectively is N. So times, now you could solve for it and then plug it in, however you want to manage that. But at this point, all of this number is N. So times R, 0.082057 liters atmospheres per mole Kelvin, times our temperature, which is 298.15 Kelvin. And we're dividing by our pressure, which we were told was 1 atmosphere. Get rid of this. Oh, little pen, where are you? Maddening. There it goes. So if I look carefully, my moles are now going to cancel because all the other moles have canceled already. Grams have already canceled. We've got Kelvin on top and Kelvin on the bottom. We've got, oh, I erased my 1 atmosphere. Atmospheres on top and atmospheres on the bottom. And now my answer is going to be in the unit of liters. Now, alternately, step 1 is find the moles. Step 2 is relate moles to moles. Step 3 is to take those moles and plug it into the gas law equation. However you want to manage that. So you don't have to throw it all into the same equation if you don't feel comfortable doing it that way. That's fine. It just, yeah, the process has to be there. And it just happens that in this case, we could just tack on the rest of the terms in our problem. So let's see what we come up with. Look right. I got 0.000953 or 9.53 times 10 to the minus 4th. And our units at the moment are liters. So what have I done this? That number seems very wrong, very small. Ah, that's right. I have a typo. Thank you. That's why I always ask you guys to. Yeah. I was thinking that number looks really wrong. There we go. 84.67. You like that better? Sorry about that. I do too. I was looking at thinking that doesn't look right. 84. There we go. 6, 7. We started with 3 sig figs, 3 sig figs, 3 sig figs. So I feel pretty good about 84.7. And our units at the moment are liters. Does anybody know what this reaction is? Sodium azide? It is a decomposition reaction. This is the reaction that takes place in an airbag. So it happens to be a very fast reaction, and that's what causes the airbag to inflate, because you're making gas very quickly from a solid. It also is why airbags are a problem. What's the other product? Mhm. What's with the substances you've made? What's the other product?
Well, there's a solid.
Well, specifically, well, nitrogen is what inflates it. What's the other product? Sodium metal, which is flammable if it gets wet. It bursts into flames. It's violently reactive. And so that's why people can be harmed by airbags, but this is still the fastest reaction that will do what we want, which is why we do use it. They do also mix in a suppressor so that it will suppress the sodium metal once it reacts. It doesn't affect the production of the nitrogen now. But the very first airbags had, could have small fire potential, or at least burn potential. Now they still have a risk. It's not like you should just deploy them for funsies, but they have a little bit of a suppressor in them now. All right, last thing we talk about in this chapter is something you haven't seen before, and it's the idea of real gases. Under most conditions, gases behave fairly ideally. So ideally means, sorry, how do I keep managing to do that? An ideal gas, stop it. There we go. I don't know if I can ever, it's just that it won't let me do the other. Figure out the rest of that word. An ideal gas obeys the kinetic molecular theory. So that's where the volume of the particle isn't significant, because the volume of the entire sample is so much larger. That the collisions inside the sample are elastic, that the particles are not particularly attracted or repelled by other particles. What if those statements aren't always 100% true? Then a gas stops acting like an ideal gas, and the ideal gas laws don't apply as well. Why would it not be true? What if they actually do interact a little bit? What if there are intermolecular forces that are acting on the particles? Some of the conditions that we can do that will cause it to behave non-ideally is if we were to pressurize the gas. We said that the volume of an individual gas molecule isn't important because the space between them is so large that they're unaware of them, of the other ones. But if I were to compress that sample, now the odds are they probably are going to encounter something else, and therefore any attraction they might have for another molecule could now take place. So if we have extremely high pressure, a gas is really not going to behave very ideally. In fact, if you pressurize a gas enough, it condenses into a liquid, which is what's actually in the tanks, gas tanks. When you're sitting behind a truck that has tanks of gas on the back, those are liquefied gases. They get a lot more of the gas into a container, small container, by pressurizing it. When you open the valve on that container, then it converts quickly into the gas form. But by pressurizing it, that's why they're all very thick wall tanks as well, because has to be a wall that's thick enough to withstand the pressures that it's undergoing. So high pressure means it's going to go more towards the liquid. It's going to start interacting a lot more. If we work with extremely low temperatures, they now have time to interact. If they're moving quickly and they just bounce off one another, then they're not going to have much of an interaction. But if they're moving extremely slowly, whatever reaction they do have, or whatever interaction they have, is going to take place more of the time. And so extremely high pressures, extremely low temperatures, no gas will behave ideally. However, there are some gases that even under normal conditions still don't behave particularly ideally. And these would be gases that actually are are attracted to the other gases in their mixture. And so if there are intermolecular forces between the particles in your gas mixture, then you can't expect that it's going to ignore that. It's going to be more pronounced at high pressure, but it could still happen at lower pressures. Now, if you're talking about noble gases, we know that noble gases don't really like to interact with other gases, so they're going to have a very low correction value, meaning that they're not going to have a lot of difference from being an ideal gas. But any gas that's polar, that has uneven distribution of electrons, actually is going to behave in a slightly non-ideal way. Second issue is if the gas particles themselves are fairly chunky, they're fairly large, then it's possible that their volume could become an issue. And so there's a second correction factor that says, well, let's look at how big the particle is. And so these constants that correct for these values are the constants A and B in this equation. These are tabulated, so you don't ever have to memorize one. And they're called the van der Waals constants. And they are specific to the particular gas you're talking about. Yeah.
Tess, do you want us to know specific laws, like this one is van der Waals?
Yes.
Combining volumes is
Yes.
Sachs, you want us to know?
Yes. Because otherwise, when you're reading literature and they talk about Gila, you have no idea what the correlation is. So they should be able to use that phrase, and you'd know, oh yeah, that's talking about the combining volumes issue. This equation is called the van der Waals equation. Now, to be completely honest, I'm probably not going to make you do a calculation based on it just because it's tedious. I do think you should understand what the correction factors are about, that the intermolecular forces will affect the pressure term, and it makes the pressure more significant. That the volume correction factor, this B term, is obviously going to affect the volume in your ideal gas law, because you can see that van der Waals equations for real gases is a modification of the ideal gas law, and it's just showing where those corrections are being made. Why do I not ask you to do it? Again, it's just mostly tedious. I would just want you to know that there are corrections and where they show up. This is in fact a graphic of if, again, PV equals nRT, and PV over RT is N. So what I've done is I've got the same amount of gas, of the same gas, and I'm looking at what happens as I increase the pressure. And you can see that helium, which is an ideal gas, or as a noble gas, behaves still in a very linear, very consistent value. Most of them behave fairly consistently. However, the ones that are completely nonlinear, those would be the real gases. These are the ones that have issues that don't follow it very well. In a perfectly ideal gas, then both of these correction terms would be 0. And that's what this is trying to show you. So the only really ideal gas has very little variation of that ratio for the same number of moles. Because again, if the moles of your sample are constant, changing the pressure on it shouldn't, on the container. I'm not saying changing how much of the stuff. So I'm not changing the pressure of that gas. I'm saying the pressurizing the container, changing the external conditions, should have no effect on how much stuff you have. That should be a constant number. It's just that when you pressurize, when you overly pressurize a gas, you are going to cause it to condense, which means you are actually going to change how many moles of gas you have now. You're not going to have as much gas because it's been converted into liquid. So in an ideal situation, no matter how much external pressure you put on it, the number of moles of that gas should be a constant amount. If it isn't, then it's not behaving as ideally. The more linear it is, the better, close to ideal, but all gases have some small amount of non-ideal behavior.
Those are the forces of that gas.
No, intermolecular forces are how the particles interact with other particles. So if I have one particle that's very attracted to another one, it can cause them to come together and start to coalesce, start to condense into a liquid form. So the more attracted they are to other, inter means between molecules, so intermolecular means between two molecules. The more intermolecular forces there are, the more it's going to act like they're being pressurized. They're now going to start to condense as if they were being pressurized. So that's why the intermolecular term shows up with the pressure, because it has the same effect as adding extra pressure to the system. All right, so that is van der Waals equation. I would expect you to understand what it is talking about, what it's correcting for. You can actually apply the numbers, and you can look at how your values for the pressure of the gas that you observe could change, but it's just a tedious exercise. So I'm not going to ask you to do that. I would just ask you to be familiar with the equation. And that is where we're going to end tonight. See you downstairs in the lab in just a few minutes here.